So in section 3.4, I really think section 3.4 is one of my favorites in the entire college algebra course. It's really cool to see how all the stuff from chapter 3 kind of connects together, and we end up really being able to see some pretty fancy stuff about some kind of fancy polynomial functions, and we're able to draw some conclusions that are pretty cool without even having to use our calculator, really. We just kind of see how some of the math connects together, and I think it's really interesting. So one more theorem we have to talk about is called the rational zero theorem. And essentially what that says, there's a lot of talk about P's and Q's right here, but essentially what they're saying is once you have your polynomial function written with your biggest exponent first down to your constant of just, plain number, if you will take all the factors of your constant, so our constant is 4, so we're going to put 4 on top, and then we take all the factors of our lead coefficient, which in our case is 2. So we're going to start with 4 over 2. 4 was our constant, 2 was our lead coefficient. Then we're going to write all the factors of 4. So think about all the different things that will multiply together to be 4. Well, it could be 1 times 4, but it could also be negative 1 times negative 4, because negative 1 times negative 4 is also positive 4. It could be 2 times 2, or it could be negative 2 times negative 2, because negative 2 times negative 2 is positive 4. So rather than think of all the positive and negative combinations, they're just going to put plus minus in front. They're going to say, hey, there's a positive 1 and a negative 1 that could work. There's a positive 2 and a negative 2 that could work. There's a positive 4 and a negative 4 that could work. So we just think about the numbers, and we just put a plus or minus in front of each number to indicate, hey, there's positive and negative versions. On the bottom, remember, we got the 2 because it was our lead coefficient. So we think of all the factors of 2. Well, the only thing that will multiply together to be 2 is 2 times 1 or negative 2 times negative 1. So that's why they have a positive 1, and negative 1, positive 2, negative 2. Okay. Then what we do is we pair all these combinations up. So for instance, it could be 1 over 1, 2 over 1, or 4 over 1. So I took each of the numbers on top, divided by each of the numbers on the bottom, and then I do the 2's. So 1 over 2, 2 over 2, or 4 over 2. Okay, now, here's why I marked out the 2 over 2 and the 4 over 2. 2 over 2 reduces to just 1, which we already had, because 1 over 1 was already just 1. 4 over 2 is just the number 2, and we already had the number 2. So they kind of did some extra writing here, but they're trying to just show us how to reduce those down. So if I take the 1 over 1, that reduces to 1. If I take the 2 over 1, that reduces to 2. 4 over 1 reduces to 4. If I divide each of those top numbers by 2, 1 over 2 is 1/2. 2 over 2 is 1, which I already had in the list, so don't include it again. And 4 over 2 is 2, which I already had in the list, don't include it again. Okay, now here's what this is saying, now that we get this list of numbers. Plus 1, minus 1, plus minus 2, plus minus 4, plus minus 1/2. Here's what this is saying, and this is what the rational root theorem is saying, is that if, big if there, but if this function touches the x-axis at a rational number is a fraction, it will be one of these numbers right here. It'll be positive 1 or negative 1, positive 2 or negative 2, positive 4 or negative 4, positive 1/2 or negative 1/2. This graph, there's no way it's going to hit the x-axis at 5. There's no way this graph is going to hit the x-axis at negative 7. It's not going to happen, because if it touches the x-axis at a rational numbers are the nice, pretty whole numbers or fractions, it's guaranteed to be one of these. Okay? And there's a proof of that in your book if you want to see it. Most people, don't necessarily care to read all that, but you can if you want to. Okay, so let's graph this. 2x to the third minus 7x squared minus 5x plus 4. And if I graph that, we can look and see where it touches the x-axis. And it looks like it touches the x-axis at about negative 1. Was negative 1 on our list? Sure was. It looks like it touches at positive 4. Was positive 4 on our list? Sure was. And right here between 0 and 1, it's kind of hard to tell just by looking. We go, well, is that 1/2? Is it 2/3? Is it 1/4? I bet you it's positive 1/2, because positive 1/2 was on our list and the other decimals or fractions in there were not. Okay? Well, who cares? Why do we care about this? Because here's the deal. Back in the day, back before we had graphing calculators, I didn't have the ability to just graph this and come up with the zeros. Okay, and go, oh, look, -1's a 0, +4's a 0. I didn't know that. But if I had a list of possibilities, could I do synthetic division with these possibilities to figure out what the zeros of this function were? Okay, so I already know -1's one of them, and -1 was on our list. So watch what happens if I do synthetic division with -1 in the box. 2, -7, -5, 4. If I do my synthetic division, zeros are my remainder, so I just verified that -1 really is a 0. But if I didn't have this list of possibilities, I might have had to sit here and guess and check numbers all day until I found a number that was a 0. Okay? So having this rational root theorem is very helpful because it gives me a short list of numbers that I could guess and check to see if they're zeros. If I didn't have a short list, it might take me forever to guess and check the right numbers to find numbers that worked. Now notice that once I have this depressed polynomial, 2x squared minus 9x plus 4, I could guess and check other numbers from this list until I found other combinations of values that worked of where this graph was going to hit the x-axis. Okay? So this rational root theorem is really powerful. Let's practice another one here. Number 1, list all possible rational zeros of this function right here. Okay? Now notice they are not telling me to find the zeros. I don't have to actually figure out where this graph is going to hit the x-axis. I just have to list my possibilities of rational numbers. Remember, rational numbers are fractions. Okay? All right, so I'm going to take all my factors of 6 and I'm going to divide them by the factors of 2. Now, why is it 6 over 2? 6 is my constant. 2 is my lead coefficient. So I'm going to take all the factors of 6. I'm going to divide them by all the factors of 2. Okay, so what are things that multiply to be 6? Well, 1 and 6. And remember, I put a plus minus in front of each one. 1 times 6 will make 6. Or 2 times 3 will make 6. So 1, 6, 2, and 3 are all the factors of 6. I'm going to divide each of those by the factors of 2. Well, the only thing that multiplies together to be 2 is 1 and 2. And remember, we put pluses and minus because it could be a positive or a negative. For instance, I could get positive 2 by -1 times -2. I could have gotten -6 by positive 2 times -3. So there's different combinations in there. All right. So then I'm going to take and I'm going to put each of the numbers on top divided by each of the numbers on bottom. So 1 over 1, plus minus 1 over plus minus 1. Or 6 over 1. Or 2 over 1. Or 3 over 1. So that's each of these numbers divided by 1. Now I'm going to go through again and put each of these numbers divided by 2. So plus or minus 1 over plus or minus 2. Plus or minus 6 over plus or minus 2. Plus or minus 2 over plus minus 2. And plus or minus 3 over plus or minus 2. So I took each of the numbers on top, divided by each of the numbers on the bottom. That's a really long list. Okay. Now I'm going to reduce them down, and that list should get a little bit smaller. Well, 1 divided by 1 is 1. It could be positive or negative, but 1 divided by 1 is 1. 6 divided by 1 is 6. So it could be a positive or a negative 6, but 6 divided by 1 is 6. 2 divided by 1 is 2. It could be positive or negative, but it's going to be a 2. 3 divided by 1 is 3. It could be positive or negative, but it's going to be 3. 1 divided by 2. Well, 1 divided by 2 is 1/2. Again, it could be positive or negative, but the number is 1/2. 6 divided by 2 is 3. I already had 3, so I don't need to list that again. 2 divided by 2 is 1. I already had 1, so I don't need to list it again. And then 3 divided by 2 is 3/2, and I don't have that one in there yet. So this is telling me that if this graph hits the x-axis at a rational number, a whole number or a fraction, it will be one of these. There's no way this graph is going to hit the x-axis at 4. There's no way this graph is going to hit the x-axis at -5. It's guaranteed that if this graph hits the x-axis at a whole number or a fraction, it will be one of these. These are the possible rational zeros. I don't know which ones work, but this is the list of possibilities. Okay? Number 2, same idea, only we have different constants and lead coefficients. So 15 is my top number, 4 is my bottom. What are the factors of 15? Well, there's 1 and 15, and there's 3 and 5. So I'm going to take each of those numbers and divide by each of the factors of 4. What will multiply together to be 4? Well, there's 1 and 4, or there's 2 times 2. So I need to take each of these top numbers, divide by each of these bottom numbers. Okay, so 1 over 1, 15 over 1, 3 over 1, 5 over 1. That's each of the numbers divided by 1. Now I'm going to have each of these numbers divided by 4. So there's the 1 over 4, the 15 over 4, the 3 over 4, the 5 over 4. And now I have to do each of these numbers divided by 2. So plus minus 1 over 2, 15 over 2, 3 over 2, 5 over 2. And now I just have to simplify them. Well, 1 over 1 is 1. 15 over 1 is 15. 3 over 1 is 3. 5 over 1 is 5. And again, they could be positive or negative, but those are each of these numbers divided by 1. Okay, then I've got 1 divided by 4, 15 divided by 4, 3 divided by 4, 5 divided by 4. Now that's kind of interesting. None of these reduced. Remember the other examples, like we had 6 over 2 and it reduced or whatever. None of these reduced because then none of them were divisible by 4. All right, then keep going. Plus or minus 1/2. That doesn't reduce. 15 halves, 3 halves, or 5 halves. Okay, this one was a long list of possibilities because none of them reduced down to something that we already had. Okay, I'm not going to worry about putting these in any sort of order. Certainly you could. That might be a little nicer if I had kind of a neat order, but it'll work. I just want to show the list of possibilities. Now notice this list is really long because 15 had several things that multiplied together to be it. 4 had several things that multiplied together to be it. I kind of like it when there's prime numbers like 2 because the only thing that multiplies to be 2 is 1 and 2. But when you have composite numbers that have other things that multiply together, you end up with kind of a long list. Okay? Same thing's going to happen with number 3. Number 3 is going to be a really long list because the factors of 8 are going to get divided by the factors of 6. Okay, well 8, that could be 1 or 8, or it could be 2 and 4. And then for the 6, it could be 1 or 6, and it could be 2 or 3. Now, if it's okay with you, I'm kind of tired of doing all this writing. So I'm going to kind of think about reducing them as I go. So 1 over 1 is going to reduce down to just 1. 8 over 1 would reduce down to just 8. So I'm kind of saving the step of writing these extra fractions and then reducing. 2 over 1 would be just 2. 4 over 1 would be just 4. And again, it's positive or negative. Okay? So I've done each of these numbers divided by 1. Now let's do each of these numbers divided by 6. So plus or minus 1/6, plus or minus 8/6. Now you got to be careful. 8 over 6 reduces to 4/3. Plus or minus 2/6. Now 2/6 reduces to 1/3, or 4/6. 4/6 reduces to 2/3. And again, you can use your calculator if you need to help reducing those. All right, so we put each of the numbers over 1. Now we put each of the numbers over 6. Now we'll put each of the numbers over 2. Okay, well 1 over 2, I haven't put that one yet, so 1/2. Now 8 over 2 is 4, and I've already got 4, so I don't need to list that again. 2 over 2 is 1, I've already got 1, don't need to list that again. And 4 over 2 is 2, I've already got 2, I don't need to list that again. So the 2 on the bottom really only added one new thing to my list. Okay, and then I take each of the numbers and divide by 3. So 1 over 3 is 1/3, but I've already got that. 8 over 3 is 8/3. I don't have 8/3 yet. I better put that one. 2 over 3 is 2/3. I already had that. And 4 over 3 is 4/3, and I had that. So this was a long list, but there were some duplicates due to reducing as I went. But those are my possibilities there. Okay? And I think that's a good stopping point for this video. We'll continue working on that in video number 2.